Okay, right. So FOMO, a formal model of memo. So hopefully you might still remember this one-word reference game that Kartik introduced this morning, right? And also this memo program that models how a speaker chooses words to effectively communicate a reference to a listener, and how the listener makes inference of the speaker's true intention. Okay. The design of memo offers a range of features and benefits, as Kartik has already told you. It allows more concise, intuitive modeling. It leads to like 10 times faster code. It integrates well with a scientist's workflow, right? So on and so forth. And just to emphasize the benefits to modeling, let's consider how this one-word reference game can be modeled in a more standard probabilistic programming language. Okay. So, and this can be done using this feature called nested inference, which is available in languages like WebPeople. So for example, here I have modeled the listener in WebPeople as a function called L. Right? This listener reasons about a speaker, by calling a mutually recursive function called S. In the listener's mind, the speaker makes two choices, R and U, okay, a true referent R and an utterance U. And the speaker chooses an utterance such that it describes that referent. Okay, that's expressed by this conditioning statement. And the speaker also prefers those utterances that increase the chance of the listener making the right guess. Okay, and that's expressed by that factor statement there. So if the listener hears the speaker say green, right, then we'd expect that the listener is more likely to infer green circle than green square, because if the speaker really meant green square, then they could have just said square instead of green. Okay. But this is what we get if we run this program in WebPeople. Okay. So the histogram here indicates that the listener cannot really make a guess between green square and green circle. Right? That's surprising, because that goes against our expectation. So what's going on here? The problem is with a subtle bug that I introduced into the listener's model of the speaker. The factor statement here has the intended effect of making the speaker prefer an utterance that increases the chance of the listener making the right inference. But it also has an unintended effect. That is, it also means the speaker prefers a referent that is easier for the listener to guess. But which referent the speaker chooses ought to be independent of the speaker's reasoning about listener. The speaker chooses an utterance for a given referent. Right? They shouldn't be choosing a referent and an utterance simultaneously. And this bug can be fixed by carefully adjusting the scope of nested inference here. And more specifically, I can fix this bug by moving the speaker's choice of a referent outside the enclosing nested inference. And now if we run this program again, we get the expected results. Okay. So all this is to just to show you that it's very easy to make mistakes when using nested inference to model rational agents. By contrast, the memo version naturally avoids this pitfall. It doesn't even have a nested inference construct to begin with, right? So it's hard for the memo programmer to inadvertently introduce dependencies that violate the principles of agency. Okay, so that's all great. But how should a programmer reason about programs written in memo? Like, what is the semantics of memo programs? We know memo is designed for modeling nested reasoning, but it doesn't even seem to have a nested inference construct, right? So now hopefully you're confused at this point. And in this work, we aim to give a formal semantics to the memo probabilistic programming language. We want to capture this kind of complex computational phenomenon in precise mathematical language. So the central data structure in the memo semantics is this thing called frame of mind. A frame tracks an agent's beliefs along with that agent's beliefs about the other agent's beliefs. And stepping through a memo program essentially evolves a tree of frames. So in this sense, the state of the program here is really the frames of minds of the agents. So let's step through this program for the one-word reference game. Initially, there is a root frame. Okay? This root frame contains only the two choices U and R, which are bound by the two axes declared in that model's header. And these choices are known to this special root agent. And this root agent has no uncertainty about the values of these two choices, U and R. The first statement of this program introduces an agent called listener. So a new listener frame is created, and the root frame contains a pointer to this new listener frame. The listener, in turn, reasons about an imagined speaker, right? So a new speaker frame is created in the listener's mind. The listener frame contains a pointer to this speaker frame. The speaker then makes two choices. So the speaker's frame contains two variables, U and R, an utterance U and a referent R. And these two variables, U and R, are not related to the U and R in the roots frame. The speaker is certain about its own U and R, right? And that's just because they are chosen by the speaker. But from the listener's perspective, the listener is uncertain about the speaker's U and R. All the listener knows is that the speaker chooses U and R from some distributions. And here we use yellow circles to indicate uncertainty. The next statement is an observed statement. This statement expresses that the listener believes the speaker's utterance is the same U declared in the roots frame. And as a result, the listener now has no uncertainty over the speaker's choice U. And finally, the listener chooses a referent R. This R appears in the listener's frame as a choice containing no uncertainty because it's chosen by the listener, but it appears in the roots frame as an uncertain choice. More formally, the frame of an agent is a triple. So first, it consists of a set of choices made by the current agent. And second, the frame contains a set of subframes. Each subframe corresponds to an agent in the current agent's mind. And third, the frame contains a set of equations that represent the conditions on the current agent's mind. Then we give a type system to memo. The form of statement typing indicates that statements are really frame transformers. So it's kind of like Hoare logic. In Hoare logic, you have a precondition and postcondition. A statement is a predicate transformer. And here in memo, you have a pre-frame and post-frame, and the statement is like a frame transformer. And executing a statement has the effect of changing agents' frames of minds. We further give a semantics, a denotational semantics to memo. A frame is interpreted into a product of two spaces. First is the space of the choice context, gamma, and the second is the space of measures over the subframes. Subframes are interpreted as measures because the current agent is is uncertain about the agent in its mental state. We can prove this statement, which says for a well-typed memo statement, if the pre-frame is satisfied, then the post-frame must also be satisfied. Expression typing is also interesting, as the type of an expression in memo tracks uncertainty. So let's look at the typing of this WPP clause. Okay? So here the listener chooses a referent R with probability proportional to the listener's confidence that this R is the same as the speaker's true referent. Okay? It's important that this probability operator be there. If it were omitted, then the listener would have to make a choice based on the probability that they cannot even evaluate, okay? Because listener is uncertain about the true referent the speaker chooses. It would appear as if the listener could read the speaker's mind to find out the true referent, or as if the speaker could control the listener's mind to force the listener to choose their referent. So both mind reading and mind control violate our understanding about agency. So without this probability operator, memo statically raises an error at that line. This checking is done by in the memo type system by tracking uncertainty in expression typing. The typing judgments track not only the type of an expression, but also the set of choices that the expression depends on. There's also a choice typing judgment for deriving if the current agent is certain about the given choices. In the typing rule for the chooses statements, we first check if so here we first check the expression in the WPP clause as well typed. We also check that the choices the expression depends on contain no uncertainty from the perspective of the current agent. In our example, the memo type system can see that the listener is uncertain about the speaker's R, so it rejects this program. But if the probability operator is there, then the uncertainty is marginalized out, right? So the memo type system accepts this program. And we give a denotational semantics to expressions too. The denotation of an expression is a measure because an expression in general contains uncertainty. But if the agent is certain about the choices the expression depends on, then we can show that the denotation of the expression is a single point mass. Okay, so to conclude, we have presented a formal semantics of memo, including a type system and a denotational semantics. This formalization is interesting because it gives precise meanings to a complex computational phenomenon, namely recursive meta reasoning between rational agents. And in the future, we'd like to use this semantics as a basis on which to formalize memo's unique compilation strategy to array programs, right, and prove that this compilation is semantics preserving. We also want to explore how this formal semantics can contribute more broadly to our understanding of theory of mind, with connections to deep open questions in philosophy and cognitive science. Okay, so I'll stop here, and thanks for listening.
Thanks, Yizhou. Do we have any questions?
Thank you. That was really, really great and really clarifying. Can you say again what K was in the frame? Like you said that a frame has gamma, phi, and K.
Right.
So what was K, and does it play into the semantics?
Right. Yeah. Right. K is really a set of equations on there are those Bayesian conditioning statements in the program, right? And the denotation, so the denotation interpretation of frame doesn't really capture the K, because K is just making restrictions on the space.
I see. This is different from the observeds statement, which causes something to become certain, right? Or
They're related, actually.
okay,
Yeah.
okay. I'll ask follow-ups.
Yeah.
So you also said that phi is the view of the frames of other agents. So how deep can this nest? Is this well-founded? Does it have to stop at some point?
Sorry. What?
So phi is a view of the frames of other agents.
Yeah.
And those other agents can have also views on the frames of other agents.
Uh-huh.
So is this well-founded or?
Oh, right. So so a frame there is really a tree where you consider the subframes. So it's a bounded tree, a tree of bounded depth.
Have you considered adding recursion to your language?
I think Kartik does have recursion in this language. It's just that we have bounded recursion, and the control flow must be deterministic, and that's the main reason why Kartik is able to compile program to an array programming language.
Thanks.
So following on the same questions, your language is first order, right? Would it make sense to take functions as arguments?
I don't think memo supports higher order functions.
Right, let's thank Yizhou once more.